My name is Dmitry Green. I'm the Chief Science Officer at Quantum Coast Capital. I'm a physicist. I actually use in my research some of the technologies that got the Nobel Prize just yesterday. I also have a second hat, a hedge fund hat. So I'm approaching this from a very commercial physics orientation. And that's the discussion we're going to have today. I think AI and quantum have a lot of synergies, as I think a couple of folks mentioned, and Alan started talking about it. AI is really, really good at doing big data problems. Quantum is extremely good at doing really complex problems. When you pair them up, it's really quite incredible, and I think we're really on the verge of something truly special when you combine the two. So with that, I'd love to have each of you go down the line, introduce yourselves, please.
Well, hello. It's an absolute pleasure to be here. Thank you to the organizing committee, and thank you, Dmitry, for stewarding us onto the stage. My name is Greg Dick. I'm the CEO and co-founder of Open Quantum Design. It's the world's first fully open source quantum computer, including hardware. We'll talk more about open source in a minute. There's such a thriving open source community. I'm happy to be part of that. My brief background is, did my physics degree a million years ago. I've forgotten what I ever knew. So I'm on the business side, but my co-founders, one is Crystal Sanko. She's a proud Floridian, and her husband, Rajbal Islam, they were both students of IonQ's Chris Monroe fame. So that's enough of me.
Great. My name is Blake Johnson. I'm with IBM. I am also originally a physics PhD, but I've spent the last 20 years leading R&D teams, and I'm currently responsible for error correction infrastructure at IBM.
And good afternoon. Once again, my name is Alan Baratz. I am the CEO at D-Wave Quantum. I had the opportunity to introduce myself and the company a little bit earlier, and so I will just pass it on.
Hi, everyone. I'm Rima Alameddine, and thank you for inviting us to be here, and thank you for all of you to here in the audience. So I am the Chief Revenue Officer at IonQ. What that means is I'm responsible for go-to-market, meaning that I'm working with customers and partners to help them embrace and leverage quantum. And just because it's pertinent to the topic of this session, I'm going to just say a few things about my background. So before joining IonQ 2.5 years ago, I was at NVIDIA for 7 years. I started at NVIDIA about 10 years ago, early in the early days of AI, and was there until it took off. And I'm so excited about what we're seeing here in quantum, and truly believe it is going to be the next wave and can have exponential impact on everything we do.
Perfect, thank you. So we have a very expert panel here. We'll talk about where are we today, and then how to unlock that value. So I'll start with you, Alan. So people often hear that quantum is far away, and you hear that all the time in the press. But D-Wave systems already are in use, as you've mentioned today. And you talked about your quantum applications, how they're realizing value already. Can you give us an example of a concrete problem that quantum has solved today, something tangible for this audience, and how AI specifically would fit into that solution?
Sure. So one of our customers is the pharmaceutical division at Japan Tobacco. And one of the things that they focus on is molecular discovery for new drugs. They use an AI approach, large language model approach, for basically generating new molecular structures. What they have done is they have introduced our quantum systems into both the training and the inference process. Essentially what they have done is they've created a smaller model that is trained natively on our quantum computer, and then they use that to generate samples. One of the things that our quantum computer is very good at doing is generating a lot of samples very quickly that are very close to, if you like, optimal. In this case, very close to the distribution for the model that was trained. What they found is that by leveraging this capability, they're able to get more molecular samples that are more well suited to human drugs. So this is accelerating their drug discovery process.
So I think, as you can see from these kind of answers, and a thread here is that data is really central to a lot of these efforts, whether it's quantum data, classical data. And so, Blake, IBM has a very long history of computing, obviously, most notably here with the personal computer, and has recently set course for new data centers with AMD. Can you give us an example of how such innovations can accelerate quantum and AI?
Sure. I told Dmitry when we talked last week that I was going to answer his questions thinking about AI in the broad, in terms of large classical computing data centers and how those participate in solving problems, including traditional high-performance computing. And one of the ideas that has emerged in just the last few years, quantum has really kind of had a transition point from kind of an experimental phase, a learning phase, building devices for the purpose of teaching quantum mechanics or learning how to build a better quantum computer, to finally we're in a phase of like earnestly pursuing quantum advantage, or we can show something better, faster, or cheaper than you can with classical methods alone. And one of the things that we realized just a couple years ago was that our best chance for finding advantage in the near term was by combining the best of classical computing with quantum computing. So that we weren't just pursuing quantum alone, but we were really combining the benefits of traditional HPC with quantum technologies. But this has introduced some new challenges, right? So just to give you an example of the kind of workflow that we have in mind, one of the sort of low-hanging fruits, the opportunities for quantum advantages in the field of chemistry. There's been remarkable algorithmic developments in how to approach chemistry with a quantum plus classical system. In particular, there are ways to partition the problem into sort of the part that the quantum computer can do uniquely, but then also offload part of the computation classically. And this introduces a new opportunity for advantage in the near term. We've seen an enormous progress as we sort of approach what is the best approximate classical methods. But it also introduces new problems, new challenges, in how do you coordinate the activity of your quantum computer with your traditional HPC center. And so our partnership with AMD is largely about building open platforms for solving these challenges. In particular, how do you orchestrate workflows so that the systems are very rarely idle, that they are high efficiency, taking advantage of these expensive resources. But then also programming models. So how do you let the developer efficiently write code, marking those sections which are sort of quantum native versus those that should be executing on the classical compute infrastructure, and to do that in a way which is frictionless, right? So that they are sort of writing the entire workflow end to end in one place, but then it gets sort of automatically distributed upon the best kind of resource that's available.
So that's actually a really good segue into open source quantum design, right? Because it takes all efforts, computer scientists, physicists, engineers, mathematicians. So Greg, being at the forefront of this transparency and democratization of quantum computing, what are some of the most exciting developments you've seen there?
At the intersection of AI and quantum, my team, so Roger Melko, he was one of the pioneers in using AI to model quantum systems. And so, of course, the team around him is vibrant and dialed in. There's sort of two things that they're really excited about. One is real-time control, and one is iterative design. So on the real-time control piece, what they're excited about, you can imagine the complexity of a quantum computer. If you've learned anything today, you've learned that it's incredibly amount of potential, but boy, there's some hard work to do. All those dials, and they interact with each other. It turns out that AI is really good at helping with those real-time control problems. And an example would be out of Alpha Qubit at Google, where they applied AI in an approach pioneered actually in the University of Waterloo, but to error correction, and with lots and lots of success. So it points in the right direction, that it's shrinking that timeline as we reach for, in deference to Alan, gate-based quantum computing. which is a little further down the road. And then the second piece that they're really excited about consistently is this iterative design. As Dmitry said, AI is really good at grappling with large amounts of data. Quantum systems, quantum machines, quantum computers are good at generating data. So there's this iterative cycle where you have new quantum systems generating their data, use AI to analyze it, assess it, and help redesign and improve and get an iterative cycle that could really accelerate the time frame to get quantum computing to scale.
So, Rima, talking about IonQ specifically, I know you've made some progress on drug design and using some of these elements that Blake and Greg and Alan have talked about. Can you talk about, from the IonQ perspective, give us some examples of these types of applications that could unlock some of the value?
Yeah, so we've been very focused on making sure that we bring value to our customers. At the end of the day, this is what everyone looks for. They're trying to advance their problems and their challenges. One of the examples is actually also in the drug discovery space, where we worked with AstraZeneca, NVIDIA, and AWS. And what we did is we took a drug design workflow and we identified the problem or the bottleneck, and we included quantum to just solve that problem. So basically, it's a hybrid workflow between classical and quantum. So you're using CPUs, GPUs, and QPUs, each one for what they do best. And by doing that, we were able to accelerate that workflow in AWS 20x. So this is real value that we are seeing today with today's computers. So today's computers, when you set them up and you have this hybrid workflow that we're all talking about, you can get value today that can be helpful and solve business problems.
Thank you. So, Alan, you've talked about blockchain earlier and some applications, and I know D-Wave has made significant progress in its technology. Most notably, recently, there was a demonstration of quantum supremacy. So for those of you for whom quantum supremacy is an abstract word, and basically people use that to refer to where is a quantum computer better at a regular computer on the same problem. Right. So can you give us some, share some of those details of some of those achievements, and especially with Bitcoin?
Sure. Blockchain. Let's start
Blockchain.
there. Okay, so first of all, the supremacy work was done natively on the quantum computer. It was not hybrid. And for us, that was really important because while many applications will require hybrid, when you have quantum and classical working together, you're never really sure what's doing the heavy lifting. But when you're running natively on the quantum computer, it's crystal clear that it's the quantum computer that's doing the computation. So the supremacy result was done natively on the quantum computer. There was no classical involved. Essentially, what we were doing is we were computing properties of magnetic materials. We looked at a variety of different lattices. We looked at a variety of different sizes for each of those lattices. We looked at different evolution times because what we were looking at was properties at the point where the magnetic material goes through what we call a phase transition. This is like water freezing. Well, magnetic materials go through a phase transition as well, and we wanted to compute the properties at that point. And we computed several different properties of these materials. For every one of those computations, no matter what the lattice, no matter what the size of the lattice, no matter what the evolution time was, we were able to perform the computation in minutes. Now, we worked with researchers around the world, 11 different institutions, experts in all the classical approaches to solving this problem, whether it's tensor networks, PEPs, TMRG, quantum Monte Carlo, neural networks, machine learning, to basically ensure that using the fastest supercomputers in the world, we used Frontier at Oak Ridge National Lab, which I think currently number 2. And as I said, all the experts to try to kind of see how you could, or if you could, perform this computation classically. The data that we collected gave us scaling parameters, and then we built theory around that, and basically came out showing that it would take nearly 1 million years to perform the computation on the largest lattices if we were to do it classically. So this is clearly a demonstration of a quantum computer doing something that's beyond the reach of classical computing. So we call it quantum supremacy. We then showed how to take that computation and use it to create a hashing function that could then be the basis of quantum proof of work for a blockchain. And we actually built that blockchain. We prototyped it. We have it running as a distributed application across multiple quantum computers today, probably one of the first distributed quantum applications. And as I said earlier, this is a quantum safe blockchain and a very electricity efficient, energy efficient blockchain.
So fascinating. And it's also very cross-disciplinary. You're pulling together on, again, just to reiterate, mathematicians, physicists on the phase transitions, and so forth. But I'd also like to relate it to what can people in the room, what kind of things can you think about from an open source perspective? So drawing an analogy to AI, some of the companies pursue open source and AI, and it's proven to be very useful in that space. So Greg, do you see, how can people get involved from that perspective here?
AI has been a really good lesson, and we can look even before AI, even in the internet, how open source has helped to really accelerate some of the innovation and access to the technology and access to good talent to play with the technology. So let me just float back just a little bit. Quantum, as you're learning, you're getting your crash course in Quantum 101, it's not a monolith. And we've heard that today, right? There's quantum cryptography and quantum sensing and quantum networks and quantum simulation and quantum computing, annealing and gate-based. And they're all at slightly different stages. So in thinking about quantum computing, gate-based quantum computing, there are still some hard problems left to solve. Hard science problems and hard engineering problems. So what our open source approach does, what the open source approach does, and by the way, there is an incredible open source quantum ecosystem here in Florida, in the US, and globally. It's really quite incredible, and IBM has been leading that charge for quite some time. The point of that, of the open source approach is you're bringing resources and talent from industry, bringing resources and talent from academia, bringing bright ideas from entrepreneurs, and maybe even some policymakers into a really low friction sandbox where everybody can work on these hard problems together, solve them, and then go away and build their proprietary secret sauce on top of them. So it's really exciting. And then earlier today, listening to the 48 graduating PhDs, which shocked me. So I can imagine that Canada, if we're in parallel, we're an order of magnitude less than that. That's not enough. This is one way to help address the quantum workforce in a real and direct way. You can imagine an open source quantum computer as part of your ecosystem alongside the academics and the proprietary companies who are doing great work, an open source quantum computer in each one of your 15 universities that signed here today. That machine could be accessible both to train the workforce in building it, to train the workforce in using it, and then being accessible to that breadth of talent, which goes well beyond physicists and engineers, to turn it into something that could really make a difference. So open source has a role to play in our view, and we're excited about it, and it's mirroring what's happened in AI.
So pulling on that business structure a little bit more, what we see is established companies in quantum. We also see numerous startups. So Blake, from your perspective, how do you see that landscape evolving? How can established companies and brand new startups work together? Blake.
It's kind of interesting from where we sit in IBM because we somehow get to sit on both sides of that coin depending on what we're doing in a given day. Obviously, IBM is a large legacy company, but our quantum effort is kind of an effort that's emerged out of IBM Research, which has its mission to be the organic growth engine of IBM. And so we are, in fact, kind of incubating a quantum startup within the larger IBM. Nonetheless, we're not just trying to build our own a new business for IBM. We're also trying to build a platform that others can build on as well. And that's where I've sort of two things that I want to say in response to this. One is that the first most important thing was to catalyze activity that was beyond pencil and paper development. right? Quantum algorithm development and quantum software development existed for almost 30 years as a purely kind of abstract mathematical exercise, right? What can I prove about how this algorithm will work? Creating a platform, a cloud accessible platform where people can access quantum computers was the first most important thing we could do to influence or spur the development of quantum software companies and quantum algorithm development, because we could turn it into an experimental or empirical science as well, right? To allow trial and error and experimentation as opposed to purely a proof-based approach to developing algorithms. And the metrics for our platform kind of speak for themselves about the success of that strategy, right? We have now over 600,000 people that have signed up to use our platform. They have executed over 3 trillion circuits on IBM quantum computers, on over 80 quantum computers that we have deployed online on the cloud since 2016. All right, so this is a platform which is accessible and which over 275 institutions have joined part of our network to say that they want to be part of this and to build on top of it. The second thing I want to say relates to the idea of open source, which is another thing which I think is critical, and I agree with Greg about kind of catalyzing development. We've seen this really since the 1990s in classical computing, that open source software can really spur and accelerate the development of other technologies. And that's why in 2017, IBM started the Qiskit project, which is an open source software development toolkit for quantum computers. Which has become the predominant, most popular platform for quantum development today. Over 74% of people that claim to be doing quantum development are Qiskit users. And that's a tool which others can build on top of. Towards this question of AI, though, all right, we understand that development is changing. Right? Developers today are using AI methods as well. They're also building AI agents, and Qiskit needs to evolve for that user. And so, like we have new projects that both kind of infuse AI methods into Qiskit's technology, like AI-enhanced compilation passes. But we also have things like the Qiskit Code Assistant, which uses generative AI to help the developer write code using foundation models. As well as things like the Qiskit Model Context Protocol, which is a way for AI agents. This is a way that AI agents can understand how they can use other computers and other services, so that for the first time, AI models can make queries to quantum computers using kind of AI native technology.
Thank you. Rima, so IonQ is now active in both all three, quantum computing, sensing, networking. How does IonQ think about that software and algorithm layer, in particular, at the intersection of quantum and AI?
Yeah, so we also see quantum and AI working together, where they're helping each other. I'm going to give you an example of something we just recently published that's really exciting, where quantum is helping AI. So we recently published this work where we took a foundational AI model, large language model, and when you're trying to fine-tune it to do another task, instead of doing that in a classical way, what we did is we replaced the last layer with a quantum layer. And by doing that, we were able to get much better performance, use much less energy, and this is particularly important when you don't have much data. Quantum computing is really efficient, and we call it expressive, where it can pull the nuances from the data much more effectively than classical methods. So when you have sparse data, replacing that last layer with quantum and leveraging quantum to do the fine-tuning is very effective. And there's so many problems like this that we deal with. Like, for example, in the healthcare space, if you're looking at rare diseases, you have sparse data. If you're doing a fraud detection, you have a small amount of data. So whenever you have that small amount of data, having quantum help AI to have a more effective model while using also much less energy is a great way to work together.
Perfect. And Alan, so coming back to AI and machine learning, I know D-Wave has recently introduced some new open source tools to facilitate the AI and ML development. Can you share more about those tools and how D-Wave is building them?
Yep, absolutely. So we introduced some extensions to our software development kit. We have a complete SDK for developing applications on our system. And we introduced some extensions to that SDK that, first of all, integrate with PyTorch, which is the Python mechanism for training models and doing inference. It's fairly widely used. And so now you can basically access our quantum systems through PyTorch. We also introduced the capability to actually train what are called restricted Boltzmann machines on our quantum system. So RBMs are a type of model for AI and machine learning. They end up being very good models, but very computationally intensive to train. And that's why years ago they were actually abandoned in favor of the more recent technologies for model training. But they're very good. Well, they actually can be natively embedded in our quantum system. And as I said, in the case of Japan Tobacco, that's exactly what they did. They basically trained a restricted Boltzmann machine within our quantum processor. So through this toolkit, you can now use PyTorch to basically build and train RBM models on our quantum computer for a variety of different applications. I should also say that we also are very strong believers in the power of AI and quantum working together. The way I like to think about it is, imagine AI being used to predict demand for products in the future, and then you might use quantum to optimize the supply chain to meet that demand. So here we're basically taking a use case and allowing each of the technologies to address the portion of the use case that it's most well suited to addressing.
Yeah, and I would just also add on a personal note of observation, as I do my own research, I think some of the biggest surprises, I think, in the academic or research community to physicists have been that they used to sort of poo-poo AI. A lot of people didn't really think of AI. They thought, oh, AI is just computer code, it's a bunch of data, you just have a computer, just crank through it, the math is simple. Well, it turns out that AI could be quite useful in designing better quantum systems, right? And that's been, I think, a major surprise to a lot of physicists as well. I want to come back to the integration point, which is another theme that comes out. And from a business point of view, integration is always tends to be a bottleneck. It's the last, you go to 90% and you need that extra 10%. Greg, from an open source perspective, so you can grab the water later, just as you were drinking. From an open source perspective, where do you see some of the biggest challenges in integration?
The team would say to me, and it's sort of in two things. One is tailoring and one is timing. So when they look at taking an AI system and using it to help solve a problem in the technological stack, you can imagine that there's very bespoke work that needs to be done. The AI that there's two things you have to do. First, you have to find a piece of your technological stack, a hardware piece that is well suited to an AI approach, and then you have to build your machine language approach specifically dedicated to that particular piece of hardware. So there's just a lot of individual work that needs to happen to do that piece. So they see that as a wonderful challenge in front of them, certainly. And then the timing piece, which bubbles up every time I push them on how fast can we move this along, is the AI requires specific timing infrastructure inside, whether as you move data to the GPU and back from the GPU back to the data set, that requires specific timing. If you think about quantum algorithms and the way they flow through your machine, they require very specific structured timing as well. And when you overlay those two different challenges, you run into bottlenecks that are challenging to overcome. So those two pieces look like hurdles, but they're good hurdles to have the community solve.
Oh, terrific. So we've gotten into some really good detail on where we are today, how we can use these tools, and where. So Rima, just coming back to some of the applications, and let's get a little bit more industry specific. Which industries do you think will first see the real world impact of both AI and quantum working together?
So the top industries I would say is first finance, life sciences, and manufacturing. And in all of those, we already have work that's happening, and we already have examples of how we're moving things forward. So just to give a few examples, like for example, in the finance space, it's really important to predict outliers, because that's what every person in finance is trying to make sure they guard against. So there's work that's being done with AI and quantum together to do that. In the life sciences space, there's so much work around drug design and discovery that we're working on. And in the manufacturing space, where we're looking to manufacture new products, there's a lot of work. I'll just give one example. Like we're working with the Navy on corrosion. That's a $20 billion problem for them annually, and working with them to figure out how we come up with better products, with better materials, so that they can overcome this problem is a problem where quantum and AI are working together.
Great. Alan, so as you guys are selling machines and you're working more and more with the industry, as this adoption begins, what should business leaders start thinking about, and in particular separating hype from reality? Because we all know that there's a lot of claims out there that kind of stretch the truth a little bit, or a little bit aggressive sometimes.
Yeah, we actually created a framework that we bring to our customers and customer prospects to help them think about what they should be looking for when they're thinking about getting involved with quantum computing. We called it Quantum Realized. We actually kind of published a piece, I think it was in the Wall Street Journal not long ago, on Quantum Realized. And there are three components to it. The first component is, does the quantum computer solve a problem better or faster than it can be solved classically? In other words, is there any example that the quantum computer you're looking at working with has been able to solve a problem better or faster than it can be solved classically? I'm not talking about faster than it can be solved on a laptop, right? But faster than it can be solved classically. Second, is the quantum system reliable enough, available enough, that you can actually use it as a part of your business operations? For example, our quantum processors have 99.9% uptime through our quantum cloud service. We actually offer service level agreements to our customers, because you can't start working with a technology if it's not available for you to use it. You can't wait a week to get an answer back, right? The systems have to be up, they have to be available, they have to be performant. And finally, are there referenceable customers? Are there customers that are actually using the quantum system to do useful work? So can the quantum computer do something that can't be done classically? Does it have the reliability and availability needed to be able to count on it? And is there anybody that will stand up and say, yeah, this thing really works? Right? I think that's what you need to be thinking about when you're trying to separate hype from reality.
Blake, can you dig into that a little bit? What should companies be doing internally to prepare for some of these innovations, particularly in the quantum AI convergence?
Yeah, I mean, I think we have to recognize that successfully using a quantum computer requires a bit of a learning curve today, right? I mean, the quantum is not yet embedded in the tools that people use day to day, right? It's not already embedded in their chemistry toolkit. It's not embedded in their financial toolkit. We will get there someday, but for those pioneering institutions that want to be part of that process of that transformation, right? they're going to have to become conversant in the language of quantum computing, right? And so there's an education journey that enterprises need to begin in order to develop that expertise. Fortunately, IBM and others have invested a lot of time in making resources that are really, really good and publicly available, right? So at IBM, we have something known as the IBM Quantum Learning Platform, which is freely accessible, that has coursework going from sort of never ever heard of quantum computing all the way up to sort of graduate school level, very advanced kind of courses, and everything in between. And that kind of can guide you through a journey of becoming conversant in how to use quantum computing effectively. And of course, the fact that we have free access models for some limited amount of use lets you start that journey as well. But for companies that really are going to dig in, they're also going to need to make some investment to start pilot projects and make proofs of concept where they'll really begin to understand use case application in their problem domains.
So, Rima, I'd like to ask the same question of you. What do you see? Yeah.
Thank you. I actually wanted to comment on something. Blake, yes, totally I agree with you. And IBM has put out a lot of tools that that lower the barrier to entry, which is great. One of the things that we're doing at IonQ is also trying to become part of tools that customers are already using, so that someone who doesn't know quantum can also take advantage of these capabilities. And just as an example, for example, Paul, we're working with ANSYS. ANSYS builds software that's used for computer-aided design. It's a $10 billion industry. So what we did is we worked with them to actually fit into their production level software. So if you use ANSYS software, you won't even know that you're using quantum. But what we're doing in the background is these hybrid workflows where that we all talked about, where you're doing some optimization on the quantum machine and then feeding it back to the CPUs and GPUs and then going back and forth. And now we're producing much better results. Like in the ANSYS case, it was 12% better results than what you would do if you would use a classical machine alone. So wherever we can either have tools that help lower the barrier to entry, or whether we can actually insert ourselves into already production tools so that customers can use these the software without even knowing that they're using quantum, are ways that we can lower the barrier to entry for everyone.
You guys have done such a perfect job of covering everything. We will definitely have time for Q&A. It's a very big topic, so I urge people to ask questions. But before we get into that, I just want to go straight down the line. Start with Greg, since you spoke last. What is the single biggest myth about quantum supremacy and AI that you would like to bust today?
So I asked the team, because they're the real experts, and the answer was clear. They said that quantum computing will not, in the near term, speed up the training of LLMs. So that's not going to happen. What is going to happen is what I mentioned earlier, that AI will certainly accelerate the development of quantum computers.
A myth I'd like to bust is that quantum computing will displace conventional computing. Quantum is not good at everything. It's not something we haven't said a lot on the stage today, but it's not a panacea. It doesn't solve all problems better than classical computers. There are certain problems with structure, problems that are related to simulating nature, where you can expect a quantum advantage, but if you take, there are certain problems that classical computers are really, really good at. If you look at simple arithmetic, for instance, the calculator in your pocket is probably a better arithmetic engine than a quantum computer, which is a kind of surprising fact, given all these marvelous things that we believe quantum computers will be able to do someday. So these are complementary technologies. They enhance and grow what is computable, as opposed to displacing and replacing what we have today.
Okay, that achieving quantum advantage is years away. It's not years away. We did it. We solved a useful problem that cannot be solved classically, full stop. It's been achieved.
So,
My biggest shortcoming is that I work too hard. Mine-
I have to agree with Alan. The biggest myth, in my opinion, is that people think that quantum is years away. We are today showing value, and the time to start is now, because there's value now, and then you could just build on it as the computers become larger and more powerful.
Yeah, I think, I personally believe we're definitely at an inflection point. And there's very few times, if you talk about regimes, so let's say I put my hedge fund hat on, when you're sitting inside a regime change, you don't know until the world is different and you look back on what happened. This is the kind of time where we can actually quantify the number of qubits we can simulate, the number of qubits we can build, and where that mathematical barrier is. So I think it's one of those very rare times when all of these things are coming together. So with that, Q&A.
Yeah, so specifically with that Yeah, so the question was to give more details around the corrosion problem for the Navy. And with that specific problem, we are in the early stages of understanding the reasons for corrosion. And actually, that was the first part that we did. And the follow-on is to figure out what we could do after that. So let's catch up after this, and I'll share with you where we're at and what we've done there.
Right, so the question is roadblocks in the NISQ era on everything that we've discussed today. Anyone want to go first?
I can start at this one. So I think Dmitry actually teed up one of the critical roadmap blocks right at the opening of this session, which is right that AI works best on big data. And quantum actually has kind of a data ingestion problem, right? Like actually how to feed data in efficiently into a quantum computer is one of the principal challenges you need to solve when designing a quantum algorithm. So one of the roadblocks is that you really have to approach problems differently from an AI first versus a quantum first perspective. That's why some of the sort of most low-hanging fruit are ones that really are, again, take a complementary approach. For instance, a predominant paradigm that's emerged in high-performance computing, which tackles kind of like the sort of absurdity of the number of options that are available to study, right? Oftentimes you may have a very powerful simulation approach, but you don't know what to simulate. And so this paradigm that has emerged is using AI methods to identify problems that look interesting. Not that they're useful, but just that they maybe are different, right? And that lets you focus your attention for your more targeted simulation approach on just those problems that you've already had some way to identify ahead of time where you're maybe likely to find something of interest. So I think for me, it's this kind of the need to approach problems in a very different way in the AI first versus the quantum first approach.
Yeah, I'm gonna chime in as well. Please. So, and I'll be a bit controversial. So when you say NISQ era, you're talking about gate model systems. That's a gate model term, noisy intermediate scale quantum. There's actually no evidence that a non-error corrected gate model quantum computer can actually beat classical on a useful problem. I'm not talking about, yeah, I mean, I could solve it better than the customer's currently solving it. I'm talking about beating classical. So the biggest challenge for NISQ is error correction and then scale. We've got to tackle error correction. And there are still very hard problems that need to be solved in that arena. And until we get there, it's really going to be hard to show gate model systems beating classical. And once we get error correction, then we need to scale them. And there are challenges there as well. So these, in my view, are the two big challenges that need to get addressed for gate model systems.
I'd like to add to this. So, Alan, I see what you're saying. but there are different modalities also on the gate-based systems. And when you look at trapped ions, they have very high fidelity and low error rates. And when you can scale them up to millions, now you can actually really get great results. So just to talk a little bit about what IonQ has done. IonQ was specifically spent a lot of time on building a software stack and accessibility and manageability and building computers. The problem that we had was scalability. And so what we recently did is we acquired a company called Oxford Ionics, where they figured out a way to change the control system from being laser-based to being electronic-based. So now the whole control system is on a chip. And actually, I brought one of these chips, so thank you for asking this question. I brought our chip with us here today. So since everything now is on a chip, we could just make these chips. You can just print them in regular semiconductor fabs, and this is how we're going to scale. And we've just announced our roadmap, and we brought it in 5 years. Everyone is always talking about how they're pushing out their roadmap. We brought in our roadmap by 5 years by being able to scale so fast using this technology. So we're going to have 2 million qubits, 80,000 logical qubits at 10 to the minus 12 fidelity in 2030. When you're at that point, you can really do big things that we can't do today. And we're not waiting until then. Every year, next year, 256, the year after 10,000, the year after 20,000. So we are scaling really fast with this combined technology.
I'm just curious. How large will that million qubit system be?
Not very large at all. The nice thing about our systems, one, is they're at room temperature. Two, they're just like they take the same amount of power as 2 air conditioners, and we're putting these on chips.
But how many ions can you fit in a trap?
We believe we're going to have about 10,000
in one trap.
And one trap. That's what the Oxford Ionics technology is going to provide us. And then after that, we also have a light sync technology, which is a photonics interconnect, which is a memory, and we're going to be able to connect these machines using this technology. So.
See, it took us 48 minutes to get going.
Honestly, I can't wait to see it.
This is great.
Seriously, 10,000 qubits in a trap? I cannot wait to see that. When you have that? Next year?
No. Next year, we're going to demonstrate 256, and then the year after that, we're going to demonstrate 10,000.
All in one trap?
That's the plan.
So I'm going to get something slightly related, but a little bit orthogonal, because we can keep this we should keep going at drinks today. I would like to add another category to the quantum computing. So we talked about gate-based and annealing quantum computers. There's also analog quantum computers, and that's related to this question. I think analog quantum computing, we're actually simulating systems. And I don't know, maybe we might need to talk about this over drinks. I'm looking at Alan's.
Well, I mean,
so I would throw analog.
Basically running the annealing protocol in a gate model processor. That's what it is.
So all I would say is there are ways to. There's more than one way to skin a cat. Once you have a good number of qubits, right? And there is progress along all of these dimensions, and I completely agree on the error correction. I was actually very happy with the Willow release, for example, which actually proved a lot of the theory. And I personally was worried before that happened that we would run into some sort of blockage where we would find some new physics when we started scaling up and couldn't scale. But luckily, there is nothing blocking us from scaling. So that's the really good news, and I believe we will get there. And there's different things you can do with these different modalities. Like simulating materials is a really big one, right? You may not even need the full suite of error correction for that, and maybe that's another point for debate after the 10 minutes is up.
I'll jump in on one point and, of course, bring it over to open source selfishly. That you can feel the energy. 3 amazing quantum companies, all doing something a little bit different, actually substantially different, but all chasing at the same goal. And we know the potential is incredible. So I'm just thrilled, actually, to be up here with these 3 amazing folks. Interestingly, in terms of this limiting the playing space to increase efficiency, to accelerate the rate of innovation. So Francesco Bova, he's an economics professor at the Rotman School for Economics. He and my co-founder recently published a paper in Nature, which specifically looked at using open source to accelerate some of these hard challenges. And the way that it works, and it mirrored what happened in AI and even with classical computing, is that what it does with all of these options on the board, when you work together with across industry and academia and those entrepreneurs, some of the dead ends fall off more quickly, and that accelerates the development. So there's a thriving ecosystem up here, and it's only got good places to go, and open source hopefully will be part of that package.
And competition will spur all of that. As we've got a little microcosm here. Any other comments, questions? Yes, please.
Of course, classical computing continues to evolve also at an impressive pace. I'd like to hear perspectives on how that constant moving of the goalposts impacts the ongoing quest for quantum supremacy.
I'll jump in here first. I mean, I guess something we haven't really talked about, I have to put my cards on the table. I hate the term quantum supremacy. I think it has really bad connotations. I'd rather talk about quantum advantage. But even in the context of quantum advantage, a piece that seems to have been missing from the conversation is the aspect of verifiability, right? If the quantum computer is truly doing something beyond what we can do with classical alone, how do we trust its output, right? And for there, I think the field has been missing an attention to this part of the problem, in addition to like this aspect of the goalposts are moving, which of course they are. I think that's maybe the second part of the conversation, that a claim of quantum advantage is really is really that. It's a claim. It's an hypothesis, and it is subject to falsification, right? And we as leaders in the quantum computing space are going to be making claims with ourselves and with the users of our quantum computers, which almost certainly many of those will be eventually shown to be false. But the power of the machines that we build and the power of the methods that we're applying is getting stronger and stronger over time, that we anticipate that the ability of the classical community to respond with an equivalent or good enough method will get harder and harder over time. So that you will start to see that instead of, a month later, the response comes from every time you put up one of these claims, the classical computer scientists get a little peeved. And it's like, oh, I can do better. And then, they go off in their office and they toil away, and then number of times they do succeed, right? So, but instead of being like next month you get the paper which kind of crushes your dream, it'll be 6 months later, it'll be a year later, it'll be, why even try? Like I can't do better. So yes, the goalposts will move, but we're going to make the classical computer scientist's job harder and harder over time. But this issue of verifiability, I think, really needs to come back into the conversation about advantage. We need to be talking about things where either there's a way to, like a short classical way to check. Factoring was one of these things where it's hard only in one direction. So if you have you've produced the factors, you can check whether you're right. But there are other things like you're doing a chemistry simulation where maybe by construction of your algorithmic approach, you can say that, for instance, I cannot have produced, my answer can only be wrong in one direction. And so, like, I can never tell you the energy is too low. I can only tell you it's too high. And then, at least if I've told you energy that's lower energy than a classical only method, then I can have a verifiable claim of advantage. So, like, I think we need to bring this part of verifiability back into the conversation.
Yeah, I actually think that's an important point. And in fact, you really should go read our Supremacy paper, because what we were able to do was to show that there are properties of these materials that can be computed classically and others that can't. And if you have the right answer for the properties that can't be, you can back into the properties that can be. And so we were actually able to show that the properties that we created actually are accurate because of the ability to back into other properties. It's a lot like factoring, but not quite. But it's worth reading the paper.
More questions? Okay, perfect. Right on time. Thank you very much. Thanks, everyone.